So we're in your chemistry and we're in chapter 5, section 4. This is the last section in chapter 5. We're going to talk about a few things though. We're going to talk about diffusion, particle pressures, and stoichiometry when we're dealing with gases. And so it's kind of quite a few things to cover right here. So I don't know if we'll be able to do it in one video. So we're going to talk first of Graham's law of diffusion. So now we got a new guy, Graham's law. Graham, new one. Just think of Graham has to do with diffusion. First of all, you have to know what diffusion is. And diffusion is like when it says when you open a bottle of perfume, then suddenly you smell the odor clear across the room and the odor spreads. That's because the kinetic theory of matter, the molecules are spreading and suddenly you can smell those molecules. But what is diffusion? What's the definition of diffusion? You have it in your book. This process, it's the process of mixing molecules of one substance through another by random molecule motion. It's mixing. And gases combining until the gas is mixed uniformly, mixed all together, and creates a homogeneous mixture. So here we have the diffusion. Well, now Graham, the rates of diffusion here. So Thomas Graham, he lived 1805 to 1869, discovered that lightweight gases diffuse much rapidly than heavier gases. For example, hydrogen diffuses faster than any other because it's very light. It only has hydrogen only has its two small molecules and the atomic weight is only 1. But it diffuses rapidly. For example, molar mass of only 2 diffuses nearly 5 times faster than carbon dioxide and over 8 times faster than xenon. But Graham didn't know why this was true, but the kinetic theory of matter provides the answer, that lighter molecules diffuse more rapidly because they are moving faster at any given temperature, right? Lighter molecules they're not so heavy, so they move faster. So when you have a lighter molecule in it, it's going to diffuse much faster. Say you have a lighter one in smell, and you can smell it quicker, and that'll be one way, than heavier molecules. And so this going on, he said the rate of diffusion, basically the kinetic theory of matter here states lighter molecules have diffused more rapidly because they are moving faster at any given weight than heavier molecules. I just said that. The lighter molecules, the lighter gases undergo more collisions in the same amount of time and spread faster. So that's what we did. So here we have the rate here. We can rewrite this equation, Graham's law of diffusion. We can rewrite this equation to compare the relative diffusion rates of different gases under the same condition and temperatures as rate 1 over rate 2 is the square root of m2 over m1. Well, what is m? Well, m up here. As a result, lighter spread more mathematically, the rate of diffusion is proportional to 1 over the square root of m. This principle that diffusion rate in any gas is inversely proportional to the square root of the molar mass. Molar mass has to do with what? Has to do with the atoms and molecules, doesn't it? So this is known as Graham's law of diffusion. So just knowing that. Basically, you need to know that. They're not going to give you any equations that you're going to have to do probably of doing the 1 over the square root of molar mass at this point. So Dalton. So Dalton's law of partial pressures. Now we're thinking of partial pressures. Partial pressures means part, right? Part pressures. So partial pressures, what is the definition of partial pressure? According to kinetic theory, gas molecules are so far apart that they have a negligible effect on each other, right? So according to the kinetic theory, they don't have much effect on each other. But each behaves as if the other ones were not there. So each expands to occupy the entire volume and exerts pressure, partial pressure. So here we have Dalton's law of partial pressure. So what is Dalton's law of partial pressure? Well, here's a picture of it. So Dalton's law of partial pressure says the pressure in a container filled with a mixture of gases is the sum of the partial pressures of all the gases in the container. What does this mean? So here is the total gases in this container. We have some nitrogen, we have some oxygen, we have some carbon dioxide, we have some H2O, which is water, and we have some argon here, and they're all mixed in here. So the partial pressures means that Dalton's is all he's saying with atoms is and stuff is that each one of these is going to be equal to the whole. So there's going to be a partial pressure of nitrogen, there's going to be a partial pressure of oxygen, all of these, and you add them all up and you're going to get the total of the partial pressure. That's all it is. It's P total equals the pressure 1, 2, 3, 4, 5, how many gases we have inside of it. So the partial pressure is the combined mixture, and you take each one of these and they're going to total. If you add all these up, it's going to total the total of the whole gas. That's all it is. It's not very hard to, but when you hear partial pressure, you think, what are you talking about? Well, you're going to talk about the pressure of just one of these. So say that we were just talking about oxygen. Well, then we're going to talk about oxygen alone here, right? But when we add the oxygen to all these other things, we're going to have the total gas being here. So here's an example. A tire was fully inflated with air. Let's see. Let me go up here, see if we can see. A tire gauge may read 35 PSI. A chemist could divide the pressure into the pressure produced by nitrogen, the pressure produced by oxygen, and so on. The total of all these partial pressures would be 35. So that means that you can take a certain partial pressure and add them up or subtract them to get other pressures. So total partial pressure equals P plus 2, P1 plus P2 plus P3, on and on. So, but the big reason we figure this out, because water vapor is a partial pressure, and it's really important that we know about water vapor. So let's look here. So we're going to talk about water vapor here on this side. So water vapor and partial pressure. So when they're figuring out, let's start here. A common technique, let's look over here first because we're going to have a table. A common technique for isolating gas in a chemical laboratory is to bubble the gas into an upside down filled with water, displacing the water from the bottle. When the sufficient gas has been collected, the pressures inside and outside are equalized, or lowering the bottle temperature, the water levels are the same. But the pressure of the gas in the bottle then equals atmospheric pressure, and the amount of gas in the bottle can be calculated by observing the volume of water displaced. Okay, so this seems like, okay, if we displace the water here, so we're displacing the gas is coming up because the water goes to the bottom, the gas comes up, so we're displacing and then we can calculate it, right? That seems very easy, but it's not so easy. You know why? This process seems straightforward enough, but it's complicated by the fact that a gas collected in this way is saturated with water vapor. Thus, according to Dalton's law of partial pressures, the gas under the condition may be found by subtracting the vapor pressure of water. So we're going to have to subtract the vapor pressure, the partial pressure of water to really get a dry gas. Because this water, the vapor of water, is going to be a partial pressure of it. So basically the P gas, this total gas here, is going to be the total gas, or the gas that we're looking for is going to be the total gas minus the partial pressure of water, getting rid of the water vapor. So, because the water vapor is going to make a difference, right? So, the vapor water, let's see, is going to be on table 5.2, which is down here. We're going to look at this table, and you can use this table. You don't have to memorize this table. But basically, it says what the temperature is and what is the pressure of water vapor at that temperature. So, at a certain temperature, say that we went to the degrees Celsius, say we went to 25 degrees Celsius, then it's going to be either ATMs or torrs. These are actually equal. I always would go by torrs because it's easier to deal with, but this would be the pressure. And so you go with whatever it is, the temperature. See how temperature affects water pressure, vapor pressure, basically the partial pressure of water in anything. So vapor pressure of water, which is the water pressure, varies with temperature. Once we know the pressure, then we know the pressure, the partial pressure, we can look that up there and we can subtract it from the total and we'll get that dry gas. And then we can use the ideal gas law to calculate the number of moles of gas. So we can't calculate moles of gas unless we get rid of that partial pressure of water that's in there, the water vapor, because water vapor is going to affect it. So we have to calculate that pressure out, and you can do it by finding the temperature and what it is to calculate it out. Okay. Okay, what did I do? Okay. Alrighty. Oh, here we go. I've got to go to the next page. Sorry. Now we have our example. How are we going to do this example? So let's do the example. We'll be done with this here. The whole partial pressure and water pressure. So we've been studying the partial pressure and the water pressure in what diffusion is, right? And Dalton's law of partial pressure. Just remember, it's Dalton's law of partial pressure, where you get P plus P1 plus P2 plus P3. So Dalton's law of partial pressure. Graham's law of diffusion. So remember, Graham had the law of diffusion and the rate of diffusion, and that is going to be 1 over the square root of m. We went over that, but we were not going to deal with that too much. Just the rate of diffusion, how different gases diffuse. And then the partial pressure is going to divide that gas up into all these different molecules like oxygen, nitrogen, and have partial pressures. So Dalton's law of partial pressures, you need to know what that is, and Graham's law of diffusion. Just remember, Graham is diffusing and Dalton is partial pressure. Okay? So now we're going to go for the example here. So the sample of oxygen collected over water is at 23 degrees. This is going to be kind of complicated. I had a hard time going through this whole thing too. So the sample oxygen is going to be at 23 degrees centigrade, occupies 485 milliliters at an atmosphere pressure of 743 torr. How many moles of oxygen? So, but you know the moles of oxygen, which formula do we have to use? Well, what was that? What was the formula? We're going to have to find out. So since we were asked for moles of gas, we need to use the ideal gas law. Remember, we did the ideal gas law. So that ideal gas law we had learned before, that was kind of complicated. It was this. The ideal gas law right there. R equals PV over ND. So we're going to be using that. And then we're going to, the R is going to be 0.0821 liters. And we're going to use this. This was the hard one. So now now we're going to find out in using this, we're going to plug this in, okay? So the gas collected over the water is saturated with water vapor. So we must first subtract that, get rid of that water vapor of 23 degrees from the table. So we remember that table that I showed you. From the total atmospheric, so that the pressure may be used in the ideal gas. So first of all, we're going to look, the partial pressure of oxygen is going to be basically the atmosphere pressure minus the water vapor. So we have 743 torrs, right? And we get that, we're going to get that from the table, minus 21.1 torr. It's going to equal 729.9 torrs, or 720 torrs. So where do we get all these? Well, it says to go, it's going to be, ask for the moles of gas we needed, an ideal gas collected over the water saturated with vapor. So we know it's 23 degrees centigrade. So let's go back to that table because that's where they got it from the table. There was our table. And it was how much? It was 743 torrs. So we're looking at, we have an atmospheric pressure of 743 torrs. That's what we gave in the problem, minus how many at 23 degrees. So let's look at 23 degrees centigrade. So 23 degrees centigrade is going to be 21.1 torrs. So we write that down, 21.1 torrs. Okay, so let's go back to the equation. So we're going to have 743 torrs up here minus 21.1 torr, which we got from the table, is going to equal 722 torrs. Now we're going to convert the units of variables to those used in R. Remember the R thing? So our equation here. So we're going to have the equation. We're going to put them all in the equation of R. So 729 torrs. So basically 760 divided, we're going to end up with 0.95. So here, let me show you it's easier to show me my how I figured it instead. So just let me hold back here for a second and I'll show you how I wrote it down, because it's kind of hard the way they wrote it down to really explain it here. So we're going to convert. So we converted by off the table here, getting 721.9 here. And so now we times that by 1 ATM over 760 torrs, because there's 1 ATM, we know, equals 760 torrs. Because remember, we always go by 1 ATM. That's the standard. So now we have to change that to 760 torrs. And so when we calculate this out and divide this by 760, we get an ATM is 0.095 on your calculator. So we change that basically. Now the volume here is in 485, right? 485. So we have 485 milliliters is our volume. That's from our equation. And so we're going to times that and change that to liters. So we have to change a lot of things in this. First of all, we had to change the volume to liters, which is 0.85 because it has to be in liters. We wanted to change this to basically torrs. So this has to be in torrs. The pressure has to be in torrs. And then now we got to change the temperature. Well, our temperature is 23 degrees. So we have to add that and change it to the Kelvin scale. And that Kelvin scale, we just added 273.15. We get 296. So now we have kelvins, because remember we have to have the absolute scale. We have the volumes, has to be in liters, so we had to change it to liters. We had basically had the torrs, and we have to change it to ATM. So we have ATM, we have Kelvin, and we have the liters, 1, 2, 3. All those have to be changed. Now we can plug those values all into our N equals P over RT, so which we developed by basically, we want to find basically looking for the moles. So we have to change this to, instead of PV equal NT, we change the R on the end. So we're using this formula, and then we put in all these. This is ATM. Put in, let's see now. We put in 0.9499. So this is actually this. I don't know why I put that in there, but it's this one. The ATM, that's the pressure. The volume is this, is 0.485 because we had to have it in liters. And then the R is this weird number that we have to put in here, is 0.0821. That number is always the same. And then we're going to put in, 296 kelvins, which is the T. So now we just cancel these all out, put this on the calculator, and we're going to get approximately it's going to be 0.0189 moles. And so we're going to put it in our scientific notation right here. This is going to be 0.0189 moles. We're going to put it in, so you can see it better. Scientific notation is 1.89 times 10 to the negative 2 moles. That's complicated, huh? Kind of a complicated one, but it's kind of fun because we can do each process and get it all done. So just mean the volume of each gas in a mixture of gases is always the same, right? And their partial pressures may not be, that they add up to it. That's the partial pressure deal. But this whole thing is pretty hard there, but they told us how to do it. And so if you have one of those, I think maybe we might on the test. We just have to make sure that we know this here, this formula. It's actually R equals NT. Then we can find any of these other values and plug them in, but we have to make sure it's in ATMs, it's in liters, and it's in kelvins. So they had to change all those values to make sure that was in the right units to do it. All right, now the only other thing here we have I wanted to go over, and this is kind of a fun thing to go over. Breathing and gas laws. What about that? So breathing and gas laws goes by, the process of breathing is a process we generally are unaware, though we can consciously regulate our breathing rate. God has wonderfully designed our bodies so that we normally do not need to think about breathing. When the rib cage expands for the diaphragm, moves in, moves down upon inhaling, as we inhale, the volume of the chest cavity increases in accordance with Boyle's law. This increased volume results in a reduced pressure in the lungs so that air will flow into the higher pressure exterior, basically. The increase in volume results in a reduced pressure in the lungs, and the air flows into the lungs from the higher outside. The reverse process in exhalation. So we're using Boyle's law that has to do with pressure and inversely proportional with volume. And that's how, because basically as we breathe in, the pressure is there to cause the air to come in, and then when we exhale, causes the air to go out through this difference. So here, look at this picture here. So we have, get my pen here. So here we have basically, as the lungs, the arterial pressure is rich in partial pressures of oxygen and poor in carbon dioxide. So that since the oxygen's pressure is high and the carbon dioxide is low, right? Then the oxygen will actually come out of that and go into the cells, because the partial pressure to equal out through diffusion would do that. The venous blood is poor, oxygen poor, and rich in carbon dioxide. So it's 40 torr, or it was 100 torr. So basically the oxygen is flowing in, as for pressures, flowing in to the poor oxygen, and the carbon dioxide is only 40 here, so the carbon dioxide is going to go out when the oxygen comes in. So when the oxygen comes in, the carbon dioxide goes out. When the oxygen goes out, the carbon dioxide comes in. So the tissues of the body, this is how we breathe. If we didn't have this Boyle's law, not necessarily, Boyle just made a law about it, but if we didn't have this, if the pressures didn't make a difference with the volumes, we couldn't even breathe. So pretty interesting. And here, even down the gas exchange in the capillaries here, we have the CO2 and the oxygens coming out to get in the vein, as it goes in the vein, and coming in through the capillaries there. So, and this is the gas exchange let me see. This is the gas exchange here, as you see. Again, the carbon dioxide in the lungs is coming out and the oxygen is going in so we can exhale the carbon dioxide. It's all has to do with Boyle's law. So, see if I can do this quickly enough. So this is the gases and chemical reactions. So basically, this is called stoichiometry because we have an equation. We're going to have an equation here. So as seen in the balanced equation, so you can find the balanced equation because we can find the molar values in the balanced equation. So we're going to write the balanced equation, convert it to volume or mass to moles, convert it to moles like we did a long time ago, use these mole ratios, and then convert the moles to the quantity desired. So let's find out what they're talking about. So these are how we can figure this out. So during the Civil War, manned observation balloons were inflated with hydrogen, which was generated on site by a chemical reaction putting acid in a metal. How many liters of hydrogen at standard temperature and pressure can be produced by the reaction of 3.27 grams zinc with excess? So it sounds like complicated, but we write the balanced equation. Zinc plus 2 hydrogen and chloride is aqueous equals zinc chloride plus hydrogen. So basically the hydrogen comes in, zinc comes in where the hydrogen was. So we convert the quantity to moles using the molar mass. So basically we have 3.27. So now we're going to take the molar mass, which is going to be 65.38 grams per mole. Remember, we can look that up. So if you look that up in the periodic table, that's what it would be with the zinc. So we look that up on the periodic table and you divide that out. So then you use the ratios from the balanced equation to convert the moles of a given substance to moles of that substance. So basically you're going to put in the zinc over the 65.38, and then we have how many moles of hydrogen to the moles of zinc. So we only have, you're going to have 1 mole of hydrogen to 1 mole of zinc as you look that. So here's basically the zinc and the hydrogen over here. And so when you calculate out, you're going to get 0.0050 moles of hydrogen. And then you're going to convert, let's see if we got this down the bottom here. So then you're going to convert the moles to the quantity desired. So let's kind of figure that out. So you're going to now do this V equals nRT. It was, so remember you need to memorize that, and now you're looking for the volume. So we have basically R equals NT, R equals was going to be, well anyway, NT over P is going to be what we're going to use. So we have P is going to be 1 atmosphere, N is going to be 0.0500 mole. See, this is what we're looking for is N. Took all this process to look up what N is. And then the temperature is in 273 kelvins. You plug them all in here, put them on your calculator, you're going to get 1.2 liters of hydrogen, right? And that's going to be that. What we're looking for up here again is how many liters of hydrogen. So we're looking at the liters, and that's how many, because we're looking for the volume, and that's going to be how many liters of hydrogen. Okay? So we'll do that when we get another problem to do that, but let's stop there.